In this video, we're going to go through lesson 11.6 on segment relationships in circles. The essential question is, how do you find the lengths of segments formed by lines that intersect circles? This lesson isn't very long, so I'm going to be going over the day 1 and day 2 portions in the same video. Let's go ahead and get started. There are 3 different segment relationships that we're going to be discussing in this lesson. The first is called the chord-chord product theorem, and it states that if 2 chords intersect in the interior of a circle, then the products of the lengths of the segments of the chords are congruent. You can see in this picture there are 2 chords. We have chord AB and we have chord CD. And notice that they intersect at point E right here. This theorem states that the products of the 2 parts of each of those chords are equal. This means that AE times EB, which are the 2 parts of chord AB, their product will be equal to the 2 parts of chord CD, CE times ED. Let's look at a couple examples now with our chord-chord product theorem. We'll find the value of X and the length of each chord. First, I'm going to just set this up. If you want to write the letters first, you can. I'm just going to go straight to the numbers here. Beginning at chord AB, you can see that its parts are 6 and 5. We know by the chord-chord product theorem that 6 times 5 needs to be equal to the product of the parts of the other chord, CD, which are X times 8. And now if we simplify that, that's 30 equals 8x, divide by 8. 30 divided by 8 is 3.75. So that is the first part of our answer, x equals 3.75. Now we need to find the length of each chord. For chord AB, we already could find that without even knowing x. The length of the full chord is the sum of its parts. 6 plus 5 is 11. Then, now that we know what x is for the other chord, x is 3.75, we can find that chord CD will be equal to 3.75 plus 8, and that is 11.75. So you'll notice that the sums, like the lengths of the chords themselves, are not equal, but the products of their parts are. Go ahead and try the try now. Make sure that you find x and the length of each chord. Please pause your video now. Here's your solution. You should have gotten x equals 3, and then the lengths of the chords, PR equal 10, and ST equals 11. Let's look at a real-world application of the chord-chord product theorem. Archaeologists discovered a fragment of an ancient disk. To calculate its original diameter, they drew a chord, AB, and its perpendicular bisector, PQ. Find the disk's diameter. Since PQ is a perpendicular bisector of chord AB, PR is a diameter by a theorem from earlier in this chapter, Theorem 11.2.4, states that in a circle, the perpendicular bisector of a chord is a radius or diameter. We can then solve this problem in the same way we just did example 1. We have a chord. Since this is a perpendicular bisector, we know that it's divided into equal parts, and both of these are 5. And then I'm going to call the missing part of the diameter x. And setting up our chord-chord product theorem, we would have 5 times 5 equals, and then the other one is 3 times x. And we can solve that now. 25 equals 3x, divide by 3, and you will get x equals 8.3 repeating, which is the same as 8 1/3. Now, that's not the diameter, remember. The diameter is all the way across the circle. So to get the diameter, which is PR, we need to add up the 3 and the 8 1/3. And when we add those up, 3 plus 8 and 1/3 is 11 and 1/3. That means that this ancient disk is 11 and 1/3 inches in diameter. And this is a cool application of the chord-chord product theorem that is actually used out in the real world. On your CYU, you're going to use the chord-chord product theorem to find the diameter of the opening of an ancient volcano that's near the island of Maui. Before we move on to the final two theorems of this section, we need to define a couple terms. First, you already heard the term secant segment. A secant segment is a segment with at least one endpoint on the circle. And a secant does need to intersect the circle twice. So you'll notice in here, the endpoint A is on the circle, endpoint E is not on the circle, and that segment intersects the circle at two places, making AE a secant segment. Now, every secant segment also has an external secant segment, and that's going to be the part of the segment that is not inside the circle, that's outside the circle. So in our picture here, BE is the external secant segment, just the part of the full segment that's outside of the circle. In our theorems later on, we're going to abbreviate the secant segment as the whole secant segment, and then its external portion as the outside. The final theorem of this section is going to talk about a tangent segment. Recall that a tangent segment is a segment of a tangent with one endpoint on the circle. A tangent can only intersect the circle at one point. And you'll notice here in our diagram that segment ED touches the circle just at point D. Point D is that point of tangency. ED, the tangent segment. If two segments intersect outside a circle, then the following theorems are true. The first theorem is the secant-secant product theorem, and this theorem states that if two secants intersect in the exterior of a circle, then the products of the lengths of one secant segment and its external segment equals the product of the lengths of the other secant segment and its external segment. That is a long sentence, and I know it's probably pretty confusing. I want us to abbreviate this as just the whole times the outside equals the whole times the outside, where the whole is going to be the entire secant segment, and the outside is going to be the external segment. And in our picture here, the whole would be like AE multiplied by the external segment, which would be BE, and that product is going to be equal to the whole other secant segment, which is CE, times the external part, which is DE. Again, that is the whole times the outside equals the whole times the outside. Full secant segment times its outside part is equal to the full secant segment times its outside part. Let's try an example here, and I'm going to encourage you to always write out the words. Notice there's two secants, and we know that the whole times the outside needs to be equal to the whole times the outside. Starting with this one, the whole segment, I have to put the 4 plus 6 together, which is 10. And the outside is the 4. That means 10 times 4 needs to be equal to the whole of the other secant segment, which I can't add those together because I don't know x. So we're going to call this component x plus 5 or 5 plus x. You need to put that in parentheses because the whole needs to be multiplied by the 5, and the 5 will need to be distributed to both the x and the 5. Now let's solve. Over here, it's just 10 times 4, 40. Here we're distributing 5 times x is 5x, and 5 times 5 is 25. And now we can just do our algebra. Subtract 25 on each side to get 15 equals 5x. And then if we divide each side by 5, we get 3. There's the first part of our question. We got x equal 3. And now that we have x equal 3, we need to find the length of each secant segment. Each secant segment is the whole segment. We already had RT. RT was the 4 plus 6, 10. Now that we figured out what x is, we know that the other full secant segment, RQ, is 5 plus 3, which is 8. Here's a problem similar to that with two secants. Go ahead and pause the video and give this one a try. Please pause now. Here are your solutions. The whole times the outside would be the z plus 13 times 13. And in the other secant segment, the whole is 30 plus 9, 39, times its outside 9. We do the algebra and get z equals 14. And then we can find the lengths of the entire secant segments by adding their parts together. JG is 27 and LG is 39. The final theorem for this lesson is the secant tangent product theorem, and this states that if a secant and a tangent intersect in the exterior of a circle, then the product of the lengths of the secant segment and its external segment equals the length of the tangent segment squared. It's a lot like the secant-secant theorem, except for a tangent segment, you don't have a whole segment and an external segment. It's all external. Let's set this up with our picture here. Whole times outside equals whole times outside. And again, this is what we're going to use. It simplifies it down quite a bit, makes it easier to find what we need to multiply together. Beginning here, our whole would be AE. And we're going to multiply that by the outside, which is BE. And that is going to be equal to the tangent squared. And the tangent here is segment DE, so DE quantity squared. That is whole times outside equals tangent squared. Let's try an example here where we apply the secant tangent product theorem. I'm going to begin by writing down the words whole times outside equals tangent squared. And first, the whole would be the secant segment. That's this part right here, QS. We need to add the 5 and the 4 together to get 9. And then the outside component is 4. 9 times 4 then needs to be equal to the tangent, which is the x, squared. Well, now we can just do our algebra here. 9 times 4 is 36. 36 equals x squared. We can undo our squared by taking a square root of each side. And that means that x is 6. Here's another example of a secant and a tangent that meet outside of a circle. And we know that when that's the case, by the secant tangent product theorem, the whole times the outside is equal to the tangent squared. Here, that would be the whole is the 6 and the y put together. When we add those up, you can either do 6 plus y or y plus 6. And then the outside is the 6. And that needs to be equal to the tangent squared. And here the tangent is that 9. And now we can go ahead and do our algebra. Let's distribute over here. 6 times y, 6y. 6 times 6 is 36. 9 squared is 81. We can subtract 36 on each side to get 6y equals 45. And then divide by 6, and you will get y equals 7.5. Here's a try now problem for you to try on your own. Please pause your video. And here is your solution to the try now. The whole times the outside, 16 times 4, has to equal the tangent squared, x squared. If x squared equals 64, we can root that and get x equals 8. And that's all for lesson 11.6. Thanks for watching. Bye.